Okay, sorry, there was some problem with the connection towards the end of that recording. What we were trying to say was, what is the need for this library mapping step? The problem is, there's no guarantee that whatever logic gates, okay, that this step has produced is available in our library. Library is, like I said, a collection of cells. Cells is nothing but older name for gates and cells are equivalent. Okay, so we don't start with nothing. We have a small library, and it's not just a picture of a gate. Okay, it's a much more information than that. A library means that somebody has not only created the layout, they have also done characterization, meaning they have performed simulations and generated the power consumption and timing information for that particular gate. So it might be a 2 input NAND gate, and its area might be, say, some zero point 0.1 micrometer square, and the power consumption might be some 10 nanowatts. So something like this. Okay, this information is available in a file called as a library, and the problem with that is it has a limited. We can't imagine that your design needs a 8 input AND gate and create the layout for a 8 input AND gate. So that's today. But tomorrow, suddenly, if somebody uses a 12 input AND gate, that might not be there. So the library is a limited number of cells or gates. Okay. So what we need to do is we need to find a way. Okay. And this means that I already gave that example. Our college library has some books, but whatever information you need is in two books. So the same way, we don't have our function directly, but we might be implementing, possible to implementing using two different gates. Okay, so maybe a 8 input AND can be used, can be using two 4 input AND gates. Okay, or if 4 input is not there, maybe two 3 inputs and one 2 input. At least that much will be there. So that's what this library mapping means. It takes our gate level netlist and converts it in terms of what is there in the standard cell library. Okay, and that produces a new netlist. So we are just going from one type of netlist to another, and that is this step here. And netlist again is a very common term in VLSI. Here net doesn't mean the, you might have, in fact, you might have seen some sort of bill. It might say somewhere net amount. Here net doesn't mean that net. Net is again one of the historic names for an interconnection between gates. You have a wire, right? In Verilog you have this data type also. So that is the same as this list of gates along with the interconnection. Netlist again is a text file. Okay, and each file will have one line for a gate, and it will say from which gate the inputs to this gate are coming from, or maybe it's coming from primary input. Okay, these are the only two options, they cannot come from anywhere else, and the output of this gate is supplied to which gate. So that is one line information for each gate. So if your design has 10K gates, for example, you will have 10,000 lines in the netlist. So netlist is nothing but a text file along with that type of information, and once you have that, you can do a simulation. Okay, that's traditionally what we have done. We will give some inputs and produce the output, and there is also a new thing here which is called as formal verification. So this is new. Pretty sure that you have not used this before, you might have heard of this, but formal verification is a completely different way of doing verification compared to simulation. Simulation, you give one input at a time. Okay, but formal verification asks more general questions, meaning can this gate ever produce the output 1010? Okay, so what would you do in simulation? Suppose you have four inputs, you keep giving all possible combinations. So four inputs means 2 power 4, 16 combinations, and you find out if it ever reaches 1010 output. Formal verification doesn't do that. Okay, it doesn't mean that we perform simulation 1,000 times and call it formal verification. It's a completely different way to do it, and it depends on a very important concept in computer science called as Boolean satisfiability, meaning does this particular uh, system of gates satisfy some condition, and it's possible only in digital because we have only two values. You cannot do anything like this in analog. It's just impossible because analog can take any values. You cannot ask questions like that. But in digital logic, because the inputs and outputs have only two values, there are some ways to check for satisfiability. That is some particular condition. Is it ever satisfied by this system or this group of gates? So that is what formal verification does. Formal verification even today is not possible for the full chip. Okay, impossible. Full chip you still have to do simulation only. But if you have some very critical, suppose the heart of your digital system is some one particular group of gates which controls everything, and that system is some thousand gates are there in that system. There maybe you can do formal verification. For much smaller subset of your full integrated circuit, formal verification is still possible, but not for the full chip. Okay, so full chip we still have to do simulation, and once that is done and we are happy with the results, okay, now we are at the zeroth level. That is, we have completed the functional requirement of our specification. Start off with the specification. Okay, we have gone through many steps, and at this point we have completed the functionality. That's all we have done. And as part of this specification, there might be other constraints also in terms of power consumption, timing, etc. All that also we have to do. So the next step is the timing analysis. Timing analysis means that um, now we have to use the layout information. This is where I said that the layout is not just the diagram of a gate. Okay, it is also the power and timing information. So some person has sat there, and again this is a job of a VLSI engineer. He has characterized, he has drawn the layout using some tools. Okay, and he has extracted. The layout is in terms of rectangles. It is in some particular material, silicon, metal interconnections, etc. But next step to that, okay, once he has verified that the input and output are matching the requirement, he has to give many types of inputs. Okay, and generate the output and see what is the delay. And we will again see this delay in much more detail, how they measure the delay, etc. But he has to measure what is the delay of this gate. So that is one number. Another number is the power consumption. So right now we are going to take that delay information. Okay, and that delay information we are going to use to do a timing analysis. Okay, so timing analysis means we have the delay. Suppose there are some 10,000 gates, and maybe there are about 100 gates in the longest part between input and output. And the timing analysis, okay, doesn't, so we already talked about simulation and formal verification. Same type of argument here also. Timing analysis doesn't mean that I give some 1 lakh inputs and find out which output produce maximum delay. That's not the way timing analysis is done. Okay, this type of analysis is based on the structure of the circuit. So circuit has a particular structure because the interconnections are there and the layout is there. Okay, we can, based on the structure of the circuit, suppose there are 100 paths between input and output. Okay, so input 1 through some 25 gates might produce output 5. Input 2 through some 25 gates might be produced output 7, and so on and so forth. Many paths are there, right? So what this timing analysis tool does, it doesn't naively give inputs and produce output. What it does is, first is it finds out what are all the paths between input and output, and say it finds out that there are some 1 lakh paths. Okay, then it orders all those paths. It also orders all those paths in terms of the logic. Okay, each of these paths is going to have a few gates. AND gate, then AND gate is given to inverter, inverter is given to a buffer, buffer is given to a another gate, etc., etc. And it orders all these paths in terms of the timing. So each gate, the layout information produce also has the timing. And since the timing is available, it can find out which of these paths takes the maximum amount, okay, for the input to reach the output. That particular path determines the delay of that particular design, not the minimum. Okay, so whenever you predict or whenever you report the timing of your design, nobody cares about what is the least time in which it produces. We are we are wanting the maximum time. That is called as the critical path. Again, we'll come back to this in more detail later on, but that is what the timing analysis does. Okay, through a structural analysis of the design, find out which path has the maximum delay, and that is the timing of the design. If it's okay, move on. Right? Not okay, see where the arrow goes back. It's like a game of snakes and ladders. Okay, the timing is not okay. Here you go back all these steps all the way back to the RTL design itself. You have to change. So these are all very critical steps to be satisfied. When that is satisfied, then test logic. We'll talk a little bit more about testing towards the end of the first part of this unit, but there are separate logic blocks that are inserted for testing also, and that produces a new netlist to the same steps, simulator common verification, and the last is power analysis. So test doesn't require timing analysis because test is a different mode of operation, meaning either you can be in normal mode of operation producing the outputs, or you can be in test mode of operation where you're testing the integrated circuit. So testing generally doesn't change the timing, so we don't need to do a timing analysis, but we need to do a new type of analysis which is called as power analysis. So very similar to what we did for timing analysis, only this time instead of using the timing information that is available as part of the layout, use the power information that is also available as part of the layout. And if it is okay, you go to the back end VLSI design, also called as physical synthesis. If it is not okay, then you're in big trouble. Re-architect. You don't even know where to go. Okay, you have to start all the way at the top level description. You have to come back here. So two huge snakes here and here, that if it's not satisfied, then you need to go all the way back to the beginning of the RTL behavioral description. So this is again very common this thing in VLSI design. Never in one shot you can go from new design to being satisfied with all the parameters. Functionality is just the beginning. We have functionality at this point, but still many things are required after that in terms of the timing and power. And only when all of them are simultaneously satisfied, we can go to the back end or physical VLSI design. So next we'll see the steps of physical VLSI design. And also in the textbook, the colloquial name in India at least, it's known as PD. Everybody knows what is PD. It's the physical design, and it refers to the steps after the final netlist is generated. We had some timing information, we had some power information, but the problem was we didn't have the actual layout, meaning that for the interconnections there was some approximations only. There were no exact values for the interconnections, and that is the main difference between front end and back end. And why this is important is if you look at a lot of studies that are happening with respect to timing, okay, compared to previous generations, maybe 1970s, 1980s, if you had a design, okay, the gates in that design were mainly responsible for the delay. But today, if you see, 70% of the delays are due to the interconnections, not because of the actual gates, because the transistor has become so small that the delay has become very less. But the problem is because the number of transistors is so high, there's just so much interconnections between these blocks, inside these blocks, etc., that the delay of the interconnection is much higher than the actual delay of the logic. It's a very strange thing, but that's how it has become today. The interconnect delay is dominating 70% of the delay in the designs is because of the interconnect, and that is not available as part of front end VLSI design. Only in the back end, these steps that you're seeing here, okay, is going to give us that particular part of the delay. And few things. First, like front end, this is also completely back end. Is based on tools. Okay, and Synopsys and Cadence are two major players in this domain. And digital only, analog layout, there are hardly any tools that will automate the layout process. People don't believe in tools still; they're still done by hand. And the algorithms also are extremely high tech, extremely complicated. Maybe in FOC, you might have heard of shortest path, etc. So many of these algorithms are modifications of that, and in general, they come under the domain called as combinatorial optimization, meaning that you want to reduce some parameter by modification, by many choices, etc. And they use many heuristics. Heuristics are nothing but they are approximate algorithms. They don't produce the exact result that is probably the best option, but in a much smaller amount of time, they are able to produce a result that is maybe 95% as good as the exact result. So these type of approximate algorithms are called as heuristics. And back-end VLSI design of physical VLSI design completely depends on these heuristics. And most importantly, they're very complex because of the size of the design. And even though we have many VLSI physical design engineers living and working in India, the programs are often running in large server farms in Singapore or somewhere in UK, etc. They're just working on a terminal, but because the size is so large that they work on server farms and they take a few hours to few days, depending on the size of their block, to produce the result. Okay, so go into the actual steps involved, again only on a high level, just because we are introducing this field, and it's very important because a lot of job descriptions are also in this domain. We just go into the steps in this automatic layout generation, which is name given in the book, but also same as physical design. At a top level, it's divided into three steps: floor planning, placement, and routing. Floor planning is a very high level activity. If you imagine, for example, an architect who has to uh, build a house, right? The first step he will do is based on the size of your plot. You might have a 60 by 40, 30 by 40, 100 by 100, whatever it is. He will decide, right, where to keep the living room, where to keep the garage, where to keep the bedrooms, what should be on the first floor, what should be on the second floor, depending on how much you want. And an experienced architect, by common sense, generally the entrance wherever you enter the hall, that will be the hall, right? Nobody will enter the floor directly into the kitchen, nobody enters directly into the bedroom. Whenever you have people coming into the house, they come into the hall. And even though for us this is almost common sense now, um, in the real estate domain at least, this also comes through experience. That is, suppose somebody is required to generate a floor plan for some type of IC, right? From many years of experience, he'll know that okay, control logic has to come somewhere in the middle of the circuit because it supplies its signals to all parts of the IC. Arithmetic logic unit is only talking to the memory unit, so you place both of them next to each other. So those types of decisions where you're placing the very large high level blocks in certain regions of your integrated circuit, that type of decision is called as floor planning. It's a very high level design. Again, it's made by very experienced engineers. Once the floor plan is decided, then overall quality of the placement, the overall quality of the layout also depends on the initial floor plan, and that is the first step. And once that is done, the next step is placement, meaning I have a arithmetic logic unit sitting in one corner of the integrated circuit. Arithmetic logic unit is composed of many cells or gates from the standard cell library. So now I actually have to put them or find a position, find a place for them, okay, along with the direction. Is it pointing upwards? Is it pointing downwards? Because the inputs from other gates have to come here. So I have to know where to give the input, right? I cannot connect the input to the output. I cannot connect the output to the input. So along with the orientation and the location, I have to find spaces for all the cells inside my arithmetic logic here. So that step is called as placement. And once that is done, okay, the last step is the routing, or nothing but you have to make the interconnections. Means that you have to form the metal interconnections between all the elements of the netlist. Wherever there is an interconnection, in the layout also there should be a metal of a certain width and length that is making that particular interconnection. That is the last step called as routing. Okay, so go through some of these steps. Is also called as in our colloquial terms called as PNR, or place and route. So that's PNR here. And if you look at this, we are talking about these two. Okay, so the book just talks about this PNR flow, and that's fine too. If you see it there, also they mention floor planning briefly, but floor planning is not given too much detail in the book. And naturally, because it's a very high level task, you might have 3 or 4 blocks, and based on the designer's experience he will automatically fix these things. Floor planning is not a very compute intensive task. These two are extremely compute intensive tasks. So the PNR flow, and even in industry the PNR flow is more important compared to the floor planning task. So we look at just those two. So again, here also it starts with the netlist, placement like we said, and the routing. Okay, plus very important, parasitics. So we mentioned that the added information that was not there in the front end VLSI design is available in the back end VLSI design. What is that information? It is the metal interconnections, and whenever you have the metal interconnections of a certain length, okay, we can extract the resistance R equal to rho into L by A. Okay, A was available from the beginning. Everybody knew what is the area of cross section, but nobody knew what was the length. Everybody knew rho because the material is fixed, it's generally copper, and L is the actual length, okay, of the interconnect based on the placement and the routing. So that was not available before, it is available at this time. The parasitic, again we have parasites in nature also. For example, the most popular parasite is a mosquito. Mosquito, actually if you look at this thing, it has no function anywhere. It doesn't pollinate anything like bees. It doesn't decompose the soil like earthworms. It has no particular function except transmit disease. So it's a true parasite. Like that, in our VLSI design also, we don't want resistance or capacitance anywhere because they tend to delay the circuit operation. But because of the circuit structure, automatically the material properties and nature of the fabrication, etc., these resistance and capacitance elements automatically are formed in the circuit. So that's why they're called as parasitics. And we have to extract that. Extract means nothing but based on the length of the interconnect, you apply R equal to rho L by A, you will get the value of R. And once you have that, you perform a detailed timing analysis. Okay, detailed timing analysis, all this information. So we have done timing analysis in the previous block diagram also, but this is with new information. Along with the interconnect, okay, is the design still satisfying my 200 megahertz clock? Before it was satisfying 200 megahertz because there was no resistance or capacitance concerned with the interconnect. But now since that information is there, we have to account for that also and still see if it is satisfying the interconnect, and if not, there is a problem. And briefly we mentioned noise and reliability, but this is a little bit beyond the scope of this book, so we'll not go too much into noise and reliability analysis here. And once all these are okay, then you can go to the manufacturer. Okay, so this is the PNR flow, or place and route flow. So just look at placement and routing in a little bit more detail before we stop this introductory class. So this is a beautiful picture showing the, so we see a lot of things here. First is you see these rectangles. Okay, each rectangle is a cell. So whoever has created the layout, he will have one constraint. What is the constraint is your cell, whatever it might be AND gate, NAND gate, 2 input, 3 input, I don't care. But it should have only this much width. Okay? This is so that when I have two or three cells, I can place them all together and I can get a nice long rectangle like this where all the cells are neatly arranged. So that is one thing about the layout. Another thing is this is one sample placement. So placement means we have placed all the cells somewhere, and these red lines, okay, these are all the interconnections that we got from the netlist. At the end of the front end VLSI design, we had the netlist. We did logic optimization and then we did library mapping also. Library mapping gave us a new netlist. This is that netlist interconnections. Okay, so there is a connection from here to here, there's a connection from input to here. These are all the inputs. This connection from this cell to this cell. This looks very bad because there's just way too many connections. So a lot of connections are going from this input all the way up to these cells in this region. So anybody who has common sense, if they had been doing this manually, okay, would have tried to keep this cell closer to this region, because one is the length is too high. Okay, the second most important thing is you see this white region in between. Okay, all these interconnections here we have drawn them as lines with some angle, but actually all the interconnections, they can only have right turn and left turn. They cannot be in a diagonal shape at all. And how many of them are there? You have to form them only in this white region here. So if there's too much congestion like this, for example, this white region might not even be enough to form the interconnections, which means that at the end of the routing step, you will get a failure signal and you have to go back and do the placement. So that's why in the placement itself, okay, not just any placement, but we want a good placement, meaning we want less congestion, we want less wire length, we want less timing, etc. etc. And this is an example where some of those constraints have been taken into the picture, and we get a much not that it's a different interconnect, it's exactly the same netlist. Okay, that's important point. Only thing is all these inputs have been distributed across the chip, and this gives us a much better placement compared to this one. So the chances that we can form a feasible routing in this case are much higher than this case. So this is what the placement algorithm does. Try to find a good placement where these characteristics are reduced. And again, there are many algorithms. Again, completely dependent on the tools. There are many algorithms which do it. Nobody does it by hand. And one algorithm I have mentioned here called simulated annealing. You can look into it, but this is modeled annealing in mechanical engineering is the way in which molten material is made into a solid, uh, along with very good strength. So annealing was uh, it was sort of I wouldn't say stolen, but it was sort of modeled after that mechanical process where we go from a bad placement to a good placement in steps. And in each steps, we do a random change and see if it is better or not. So that is one way in which we go from a bad placement to a good placement incrementally using a algorithm called as simulated annealing. Oh, parasitic extraction. Again, we mentioned this. Very natural. What it means, based on the interconnection, they will have some length and width, and based on the properties of the material, based on the length of the interconnections together, we can extract the R and C. Together, the size and the material and the model also, based on the equations that we're using, we can extract these values from the circuit along with the routing information. Routing information is very important for parasitic extraction. And this is an example where we see routing. Routing is very, very important task, because if the routing fails, right, whatever else you have done has to be changed. And it can go all the way back to the beginning of backend VLSI design also, where we have to change the floor plan. And this is one example. Obstacle here means that already some wires are there in this region. So here we have some standard cells. So this white region that you see here, okay, is nothing but your white region here, and you have standard cells on top, you have standard cells below, and you want to form an interconnect between this and this. So for us, just by seeing it, it's very easy, but it's not so easy to do this thing, and there are many complicated algorithms, maze router, channel router, etc. And there are many constraints also. If you have wires too close to each other, they might be short circuited, which means that you will have wrong functionality. So all those things also have to be taken care during the routing process. So we'll stop here now and we'll continue in the next class. Okay.